Hey guys, welcome to Great Learning. Now, analysis of variance is such an interesting concept that I am very sure that all of you all are very curious to understand. Now, the terms such as mean, median, mode, all of these form to be a very important foundational part about statistics. Now, as you are already aware that we can use statistics, we can apply the concepts of statistics to eventually perform a lot of different tasks. Now, when one of these tasks is somewhere on the lines of data analysis, data engineering or anything of that sort, you have to understand that analyzing the differences that exist inside your data and between each of these entities will give you more clarity, not just about you having a better understanding of your data, but at the end of the day, you having that understanding will help you produce better results, eventually churn better numbers, and at the end of the day, ladies and gentlemen, you will have better insights and maybe a more predictable outcome in a more structured way. Right now, in the world of information technology, whenever we tend to use any of these concepts to actually derive a solution, we tend to look at all of these things. And the best part about analysis of variance is that it is actually a very simple concept, but somehow beginners and newcomers stumble upon understanding what this actually is. Now, ladies and gentlemen, we here at Great Learning have understood this problem, and we here aim to help you guys to make sure that you have complete working knowledge, complete foundational knowledge about what ANOVA is, or analysis of variance, right? Now, both of those mean the same thing, and I'm sure you guys are excited to understand this, right? Now, ladies and gentlemen, I'm going to be giving you an ample amount of examples, a lot of examples all the way through, so that you have complete understanding of the same. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleagues, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments. Well, what are we waiting for? Without further ado, I think it's high time we take a look at the course agenda. And of course, I welcome you all to this course, guys. My name is Anirudh Rao. Here's the agenda for you all. Now, coming to the course agenda, analysis of variance, ladies and gentlemen, we are trying to take an approach where we are trying to ensure that you have a concrete understanding of the same. Now, whenever you have to revisit a concept later during your advanced phases of using ANOVA, there will come a point of time where it will test the strength of your foundations. To make sure that your foundations are very strong, we're going to start this out right from the absolute basics to understand first of all what is analysis of variance, right? Now, we're going to take a look at it from the most basic perspective, ensure that you have the strongest foundation. And once you start getting to understand what ANOVA is, once you start getting to understand what the analysis of variance is, the next thing is that you'll be very curious to know about certain terms that gets thrown around in the world of ANOVA. Now, I'm sure you might have seen those terms, and I'm sure you might have been left a little confused because those terms, they seem very complex, and if you do not understand a couple of these terms, it becomes very difficult for you to have to picture an entire puzzle at hand, right? So to make sure we're clear with that, we are going to be taking a look at some really important terminologies in ANOVA, and after that is done, one more important concept actually, is very critical for you to understand ANOVA, which is hypothesis testing. Hypothesis testing is again, one of these concepts that is really simple to understand, yet it is seen to be very confusing by, people who are new into the domain that we're speaking in. Don't worry, we're going to be understanding all of that. I have fantastic examples lined up there as well. Now, once we understand what ANOVA is, once we understand the important terminologies that govern this particular domain, and you have other domains which form to be slightly a prerequisite. Hypothesis testing is actually a prerequisite that you should know when you're working your way into ANOVA. And once you're clear with these prerequisites and you have a solid understanding, we're going to be having a deep dive into ANOVA to understand what it has to offer for us, and we are going to have a ton of fun understanding ANOVA to a good amount of detail. Now, after we've had a chance to take a look at ANOVA, the next thing, again, another point where things can seem to be slightly confusing for beginners is when you tend to look at understanding one-way ANOVA, two-way ANOVA, and of course, there's a concept called MANOVA or MANOVA, which basically talks about multiple analysis of variables. Now, I gave you a short clue there. It's a very interesting section. So I hope, ladies and gentlemen, with this, you are very clear about the agenda for this particular course, right? Now, with that, I think it's high time we get started with the first item on the agenda. Now, ladies and gentlemen, coming to the first item on the agenda, which is what is analysis of variance. Now, ladies and gentlemen, I want to have one of these concepts really clear with all of you all. Now, throughout the course out here, I might be calling analysis of variance as ANOVA, A-N-O-V-A, ANOVA, right? ANOVA and analysis of variance, as you figured out right now, is exactly the same thing. So what is this concept that we are taking a look at? And the most important question is, why is it so relevant that you have to know all of these concepts, right? Well, let's take an example approach to help you understand the concept. First of all, let's just say that you are, you're a businessman and you're willing to get your cars painted. Let's just say you have 3 old cars. Think about it to be maybe repainting or maybe polishing, or any of these activities will make sense. So you're a businessman, you're always in a suit, you're in a tuxedo, you want to look great, and you want to walk out of a car which eventually looks great as well, right? You don't want to be the most fancy looking businessman coming out of a car which looks pretty dirty, right? It won't add to your maybe image or whatever it is. So what you say is, hey, I have 3 old cars, I want them repainted or I want them repolished or something like that. And the key highlight here is that you're a businessman. So once you're a businessman, you want your cars at the earliest, right? You cannot be left stranded without a car, nor when you're a very high standard, when you're in a very high position, people usually rarely take taxis out to their work. Common assumption. Or let's just say in a hypothetical example such as this. Now, what would you do in this situation if you want all 3 of your cars to be ready and, if you want it quicker, you will just prefer a painter or a polisher who will do the job really quickly and who will do it better, right? So, among these 3 cars that are being painted, maybe the one you'll really like is the one that gets painted quicker, the one that has a job which is really well done. Again, common sense, right? Now, what if your car, out of these 3 cars, let's just say one car is actually really good. It probably doesn't require repainting or repolishing or anything. It just requires a good wash and then a detailing job or something like that, right? It doesn't take a lot of work. Let's just say that. And there's another car which you've probably used daily for the last 2 years. It has never seen water. It has never seen, it has never been cleaned basically. So that car will take a lot more amount of time and work to actually bring it back to its original glory. Now, here is where the question lies in. One of these painters would have taken less time to probably do the same job, but another painter would have to take a lot of, basically take more time, because at the end of the day, his or her car might require a lot more work. Now, when you try to generalize and say, hey, I gave 3 of my cars to be painted or to be polished or something, and when I got it back, one of the cars came really quick, but the other one took a really long time. So when you tend to analyze a situation such as this, when you ask, okay, why did this happen? Why did one of the cars come out really quickly while the other car was stuck in the paint shop for a really long time? Can you just say that all 3 painters had the same effort put in? That would be slightly difficult, right? Because one car did not take so much effort. Maybe the middle car took a good amount of effort, but the other car, you drove it daily. It was an absolute horrible shape that needed a lot of fixing. Now, that guy, the third guy, would have worked a lot more probably than the first guy, right? It's a common assumption. We can assume that. But what happens is that when you have to make a decision, when you have to say maybe which of those painters you would like to go back to for the next time, for the, let's just say polishing or something, that you want to go back to them, you want to make a reliable decision. You don't want any guesswork. And of course, if you don't want any guesswork to understand the concept, what are you going to do? You're going to require some evidence to support saying this painter was better than that one. Guess what technique is used in a situation exactly such as this, right? So whenever we talk about ANOVA, analysis of variance is a really popular technique that will help in making these critical decisions which are important. Now, I might have given you an example which does not highlight the importance of ANOVA, but at the end of the day, this is a concept that is used, I want to say, by almost every single company that exists out there who are trying to analyze something, right? Because ANOVA is a concept that will help you take a data-driven decisions. And when I say data-driven decisions, you have to understand that you're no longer guessing. You're no longer saying, I think this might happen. You will say, hey, I know this will happen because I have the data to prove that that will happen. Now, if you were on the other side of the conversation, what would you like to hear? Do you want to hear that I just guessed out what might happen to an analysis, or I come with proof and I come with some data to say, hey, I know what will happen and here is concrete evidence of what's happening, so you can use it to take your decisions? Which would you prefer? Especially if it's a very, very important decision at a really high managerial post or something. Of course, you'll go with the person who brings data, who brings proof, who brings validation, who brings evidence. Correct? Now, to get to that point, to eventually make that decision, to analyze what went wrong, what was correct, and to have a structured, unbiased and almost unbiased approach of how to get this done, ANOVA is really, really popular for this. Now, it's one of these statistical techniques that usually trumps a lot of other techniques that we have out there, because whenever you're trying to compare something, you usually break it down into its simplest terms, right? If you're trying to compare fruits, you'll compare an apple to an orange. So you have to pick up individual entities to compare. But in ANOVA, the biggest advantage is that here you have a technique that will help you assess and analyze multiple groups of data at a time, right? Now, there are multiple groups of data, meaning it will have its own averages, it will have its own mean, median, mode values and everything. And when you say that something is varying there, all you're trying to do is you're trying to have a fixed point. In many of these cases, it's usually the average of the mean. And all you're going to do is you're going to take that mean and eventually find out what are the difference between a group which has one set of mean values and maybe another group which has another set of mean values, right? This technique, once you start applying and find out what is the average time or something that took for these maybe painters to work on your car, you will get to find out at the end of it with concrete evidence to say that one of the painters actually had an advantage to begin with, right? And if all three of them were maybe provided an equal car, then too you would find some difference in maybe human error or the way the painters would work or something like that. But at the end of the day, you think that there's an equal chance at completion of task. But once you perform analysis, you will understand to a good amount of depth that one guy took a lot more work, took a lot more time to do it because there was a lot more work, and the other person might have not taken it, right? Now, this works exactly similarly when you think about it in the IT industry as well. When you have a huge team working on common operations and you want to have a threshold, you want to understand if your team is slacking off or if they are working at their best performance, you can use the concept of ANOVA to actually analyze a lot of things that they're doing to see if everything is on track, to see if somewhere is lagging behind, or in a very rare case to see if you're ahead of your schedule as well, right? Now with these many points that I have mentioned, I am very sure you have a clarity about what ANOVA is, and it's not just about what ANOVA is, but how important it is, right? Right from maybe you having your car painted all the way to the executive decisions that happen in Fortune 500 companies. Everywhere ANOVA is super popular. And while you're watching this course, I can bet to say that there is someone out there right now. In fact, there'll be multiple people out there right now who are using these concepts as we speak as well, right? So it's really important for you to understand that. Now, for some of you all who might have not gotten full clarity, let me give you some more examples so that you can relate to the concept better. Now, let's just say that there are students from multiple colleges taking the same examination. It happens if you're a part of a common university, right? Now, there's many universities here in India. A popular one in South India is VTU. It's called Visvesvaraya Technological University. Now, based on those universities' norms and all of that, there are colleges which link themselves and associate with respect to that university. So all these people who are a part of those many colleges, at the end of the day, will be taking the same examination that is set by the university. Now, here you can actually use ANOVA in a very interesting way. Here you can actually use ANOVA. Since the tests are the exact same thing, you can directly take a look at comparing colleges and to see which college maybe performed better than the other one, right? How amazing is that? It sounds like a very simple concept, but when you actually see the data and when you have to get to do it, it can be seen as a complex task. But with the help of ANOVA, you can simplify it to a good amount of extent, right? How cool is that? And then let me give you one more example. Let's just say that you're starting a farming business or any other business, and now you want to understand what processes should you do to have a better yield compared to the other. Maybe should you set up rainwater harvesting, or maybe do you have to change the way you put fertilizers in your field? Maybe you have to start moving around soil. So there are so many processes, right? Now I'm not a farmer, I have no idea about this business, but I am very, very sure there's a million different things which will have a huge play in the outcome, right? You know what happens, right? If there's a drought and if the rain is delayed by a couple of days, the crops vanish. It's all a waste of time. So it is very important for you to analyze all of this in depth to make sure that you're getting ahead of your business everywhere, right? So it's really, really critical to understand this. Now let me give you one more interesting example. Let's just say that there is a person who is diabetic, right? And there are 3-4 various treatments that has been suggested from various doctors. One doctor says, hey, why don't you try Ayurveda? The other doctor says, hey, why don't you try some of these hardcore medications that have worked previously, or something like that, right? There's a lot of doctors giving you a lot of opinions. One other doctor would say, hey, why don't you just get up and start walking or something, or be more active? That way you can have all of your parameters under control. Now, if you are on the other side, and if you're a very interesting data analyst, what you can basically do is find out which doctor has given you really good advice. Now, no offense to all the doctors that are out there. It's just the fact that you can have a chance to track these metrics and you can understand for yourself which process might work better. I'm not saying you're comparing doctors to find out which one is better, but what treatment works better for you is the discussion here. And that you can easily find out with the help of analysis of variance, right? Now you can see this, right? You might have thought about a situation where analysis might not be required, or you might thought of a situation where ANOVA might not have such levels of importance, but when you actually get down to it, you realize that it definitely has a lot more impact than you might have initially thought about, right? So let's talk about a little bit about what is required to understanding an ANOVA. Now, as I just told you, ANOVA is a really popular concept in statistics. So of course, you have to have a basic understanding of statistics. You need to understand how the world of statistics works. And more importantly, no one is going to ask you a question saying, hey, prove this theorem or prove how this works. What knowledge you require is for a fact that you need to know how to apply these concepts to get there, right? And then understanding measures of central tendency. Measures of central tendency sounds like a very complex concept, but at the end of the day, it's mean, median, and mode. You've studied all of these in primary school, I'm very, very sure, or if not in college as well. But knowing how mean, median, and mode works is very, very important, because once you understand mean, median, and mode, then comes variance, then comes standard deviation, and all of those concepts, right? It's built on top of each other, so it's very important for you to know. And then basics of hypothesis testing. Yes, hypothesis testing is also very, very important, because when you're trying to assess and analyze multiple variables, and usually when you do it at the same time, things can get a lot confusing. So you usually, when you're working towards a solution, you start out with certain assumptions in your head, a hypothesis, let's just say, right? So you're going to require some understanding of that. And don't worry, we'll have a section where we'll have a quick look at understanding hypothesis testing. And of course, once you know statistics, once you know how to apply these concepts, and once you know how to prove everything on paper, what is the next thing that you want to do? The next thing is you want to translate all of your results to make sure you can use the power of your computing to maybe have a widespread impact of the solution as well, right? So of course, taking your own data analysis knowledge and putting it into code, either in the form of Python, or we have another brilliant tool, Microsoft Excel. Now, Microsoft Excel is absolutely brilliant, yet at the same time, not a lot of people use all of its capabilities. So it is usually put on the back burner, and people say, hey, Excel is only for workbooks. Not really. Excel is a very, very, very in-depth data analysis tool. If you know how to work with 100% of Excel, trust me, you can call yourself a data analyst, because there are so many things that Excel offers us. Just that the widespread population probably, in my opinion, uses 20 or 30% of what the entire tool offers. So if you master those extra 60-70%, trust me, it's a beautiful, it's actually a very powerful tool. Of course, there are better tools for analysis, there are better tools for business intelligence and whatnot, but you cannot state for a fact that Excel is not powerful, right? So having the knowledge of all of these is very, very important for ANOVA. Well, with that, we are done with our first section. Now, coming on to a section where we're discussing some of the really important terminologies in ANOVA. Now, look at these terminologies that you see on your screen, because I am sure that there might have been a point where you're probably learning ANOVA on your own, that you've seen these terms and it is very difficult to make sense out of them. What does a grand mean mean? I mean, you would have just learned what a mean is right now, and now someone's asking you what a grand mean is. There's something called group variability. There's something called F ratio. All of these, as a beginner, even if I were to look at it for the first time in my life, I would be pretty confused, right? Now, I've been doing this for like many years, and I still remember the day I would have been, I would have been taken aback by looking at these terms. And to make sure it doesn't happen to you guys, here is what grand mean means. Grand mean, basically, right? Let's just come back to the basic definition of what a mean is. Mean stands for average, right? We know that if you have 10 numbers, if you want to find the average of 10 numbers, what do? You add all of those 10 numbers, you will get the sum of it, and you will divide all of it by the number of elements. In this case, it's 10, right? You know how to calculate an average, you know how to calculate a mean. But in the world of ANOVA, we have two popular means. It's not just one mean that we say average, you're done. No, here we have two means. One is called the separate mean. The other one is called the grand mean. Now, a separate mean is basically you taking the mean, you taking the average of certain sample units that you have in consideration. 90% of the time, you have a huge data set. What you're going to do is from that population, you pick up sample sets, right? You pick up small amounts of data on which you perform analysis. If you perform analysis in a correct way, you can sort of say that, hey, if it works on this sample population, if it works on this sample set, it might work for the population as well, right? So a separate mean is when you find mean for each of these individual units or each of these groups of data that you are interested in. But what about a grand mean? Well, think about it like a grand finale, right? What happens in a grand mean is that when you have multiple individual means which are already there because you calculated it manually and you have like 100 different means right now from your data point, you take all those 100 means and you can take the mean of those means, right? Mean of all means is basically the grand mean. You take each of those means, add all of them up, divided by the total number of means that you just handled, and what you have at hand. What you have at hand right now is the grand mean, right? It is basically the mean. It's basically the average of all other averages that you have observed, and you've basically taken like a lot of averages, combined it into one big number and one big average, and that average is called as the grand mean, right? So that literally is what grand mean is, and it's as simple as that. Next, let's take a look at between group variability. Now, let's just say that we have certain sample data and we have multiple overlapping points, right? Now, if you have certain sample data where the data elements are literally around one single point or around 2-3 different points, when you try to find an average, you will realize that the average of each of those points will not differ by much, because all of those are like clustered onto one single surface, or it's clustered into one simple set of group that eventually will not let you have multiple means. That's the first thing that you have to understand. So finding your sample means or finding even something such as a grand mean will not make sense, because if all your sample means are similar, your grand mean will be one big number, which is again pretty similar. So it will not give you the in-depth clarity that you require. So what you do then is you chuck away the simple mean, you chuck away the grand mean, and here you understand the variation that occurs in between these points where there is overlapping occurring, right? As I told you, there's a couple of data points here, there's a couple of data points. In this case, they are overlapping. What you do is you try to find the variation that exists between those points which are overlapping. The overlap is your problem, right? That's where all the confusion started. But what you can do is find how different is each element in that particular region where it's overlapping. And again, a concept of standard deviation, how far away is your point from a mean or from a variance, something like that, is what will give you complete clarity, right? You take a sum of squares and you eventually work on it to you go from variance eventually to standard deviation. Standard deviation and variance are just one square root away. I'm sure you might know the formula already, but knowing that wherever there is overlap and the variation in the mean that happens at that overlap, that point is called as between group variability, because two different groups overlap. You try to find out what's overlapping, find the variability in the overlap, you're good to go. That again, as I just told you in the last 5 minutes, is between group variability. So the next time you see this term, I am confident that you will know what it means. Right? Fantastic. The next important terminology that you really have to know about is something called as the F ratio. Now, F ratio is basically a measure that we have, which is a very interesting measure, because here what we're trying to do is we're trying to check if all the means of multiple samples are significantly different to one another. Now, if you have multiple means from multiple samples and you want to understand if there is a huge difference that exists between these 2 points or multiple different means out there, F ratio is what is a number that's going to tell you how different is your mean from each other. Now, if this ratio, it's a ratio, right? If this ratio is actually lower, it means that your sample means, the samples that you have taken from multiple points, are pretty similar. But what happens when your ratio is high? You can pretty much take a guess, right? But again, when the ratio is low, it's very important for you to know that there is one concept called null hypothesis, which you cannot reject. It cannot be rejected at this moment of time. I know some of you all might not know what null hypothesis is. Just hold your thought for a second, because we're going to be discussing that as well. But know this at the moment. If your F ratio is low, it is vital for you to understand that your null hypothesis cannot be rejected, right? And the F ratio basically uses the measures of between group variance, and there's another concept called as within group variance. These two concepts are very important to understand how the F ratio works as well. Now, we checked out one of these measures between group variance. There's another measure that you can go about understanding now that you already know between group variance, which is basically within group variance, right? So it's pretty similar, yet it's radically different. And I want you guys to spend some time understanding what it is and how that has an impact for your F ratio, right? Fantastic. Now, we understood that the F ratio has a certain say to, to basically be dependent on the world of hypothesis testing. So what is so important here that you have to know in hypothesis testing, without which it would become difficult for you to understand ANOVA? Well, the first thing that I'm going to tell all of you all is that hypothesis testing is not just an important part of ANOVA, but it is actually a very critical part of applied statistics in itself, right? So what is hypothesis testing to begin with? Well, hypothesis testing is one of the part of statistics where you try to make an assumption. You make assumptions even before you start working on a solution, and you have a very structured set procedure in hand that will help you test your assumption to see if your initial assumption that you might have made is either correct or is incorrect. If your initial assumption is correct, you say, hey, I accept the hypothesis. But if your initial assumption was something very wrong, and you can later prove it with respect to data to say you were wrong, there's absolutely, you reject your own initial assumption, right? Because whatever you assumed were wrong. How do you know that? You now have the proof. You now have the data to actually tell you that you were initially wrong, right? That is very simply what a hypothesis is. But in hypothesis, when we try to apply hypothesis, again, there's two types of hypothesis you really should know about. One of the terms you just heard in the previous slide, null hypothesis, and there's another term called alternate hypothesis. Well, what are these terms? Let me give you an example to actually explain the situation. We all know our solar system, right? We all know our solar system, and we know that we have a very nice planet at the end of the solar system. It's called Pluto. Now, some of you all are saying, oh, Pluto is not a planet. Now, some of you all are saying Pluto is a planet. Well, what's the actual deal? Well, when probably people were trying to analyze, when astrophysicists were trying to understand if Pluto was a planet or not, initially they would have assumed something. They would have said, hey, if a celestial body has so-and-so size, so-and-so shape, and maybe it has this many diameters worth in so many thousands of kilometers or something like that, that's when they say that this is basically called a planet. Starting, if you remember, when we were kids, probably a couple of decades ago, they would have taught you that Pluto is a planet in the solar system. And then there were a couple of discussions to say, oh no, Pluto doesn't meet certain requirements to be able to call it a planet. So we won't call it a planet anymore, right? There's a lot of confusion. So you can see that the initial hypothesis, the null hypothesis, was that you would say that, hey, I begin by saying Pluto is a planet. It's called H0, or it's called null hypothesis. And then there's an alternative hypothesis. This is not you just basically telling something out. This is not you just taking a chance. This is you knowing that your alternate hypothesis will probably be affected by some other situation, by an external factor. So you cannot guess an
anything in the alternate hypothesis. Your null hypothesis, yes, you can guess and try to prove if your guess is right or wrong, but your alternative hypothesis is used, and you know for a fact that anything that you change might have a say in your result, right? So basically it's denoted by H1 or HA or something like that. So these two concepts, null hypothesis and alternate hypothesis, always take the center stage whenever you are trying to understand anything related to hypothesis testing. Now there's many other metric, F score, T score, so many scores and so many tests which will tell you if you should reject the null hypothesis or not. And we know for a fact that if the F ratio is less, let me quickly go back to that slide. As you can see, we know if the F ratio is low, it basically means that null hypothesis cannot be rejected. Now one more thing you have to understand about hypothesis testing is you don't say we accept the hypothesis, you just reject the other one out for some reason. That's the colloquial term you would go about using. Now, you might be a person who's saying that, hey, the process to determine whether you have to reject a hypothesis or maybe to fail to even reject the null hypothesis, what is this process called? The process where you reject the hypothesis and have a conclusion at hand is basically everything called hypothesis testing. It involves 4 important steps, as you can see from your screen right now. And the first step in any hypothesis testing for any solution out there in the entire world is for you to define what a null hypothesis is and for you to define what the alternate hypothesis is. Because once you understand and figure out these concepts and you define them, that is how later you can have a plan. That's step number 2. Step number 2 basically talks about you having an analysis plan for you to use sample data to find out if your null hypothesis is right or wrong. Once you do that, you come to the third step. The third step is pretty simple. You'll do some analysis to find out if you have to create, if you have to create a single number, and that single number is usually called as the test statistics. Later, fourth step is where all the magic happens. You understand the result by actually applying the decision that you took, the decision rule that was put into place to check if your null hypothesis is true or not. If it's true, you know what to do. If it's not true, again, you know what to do in either decision. There's no more guesswork from that point. Guesswork is usually in step number 1 when you're trying to define the hypothesis. And once you've defined those hypotheses, there is a very structured way, as you can see from step number 2, 3, and 4, that you can actually work through and say that, hey, it was an assumption until then, but now I have concrete data to no longer call it an assumption, but call it what? An observation, right? So that is really important for you to know. So there is a metric which is used to track. It's called as the T statistic metric. And usually if this value of T statistic is actually less than something what we call as the significance level, then we say, hey, null hypothesis doesn't work anymore. I want to reject the null hypothesis. Or you say that you fail to reject the null hypothesis based on whatever condition we have at hand otherwise, right? Now, technically what will happen is that you will never say that you will accept the null hypothesis. You will either say that you fail to reject it or you fail to reject the null hypothesis itself. That, as I just told you, right, it's a colloquial term of how you would say it. But of course, at the end of the day, it does have profound impact on what it means as well. So this is a bit of hypothesis testing that you really should know about. And then coming to certain 1 or 2 really important terms that you really have to know in hypothesis testing. The first term that I just spoke about a minute back is significance level. A significance level, when you say something is significant, you know that it has certain importance, right? So here what we're trying to do is basically significance level is nothing but the probability of when you should reject a null hypothesis, but in actual it might be true as well. So to give you an example to help you understand this concept better, let's just say that there is a 0.05 significance level, which basically at the end of the day means that there is a 5% risk in assuming that there is some difference. But in actual, there will not be any difference. But you say that there's a 5% risk. So this is that 5% risk you associate is basically called as a significance level, because you're not just saying, hey, there's a risk. Now you're saying there's a 5% risk. You have a way to measure that. And that significance level is a very important term in hypothesis testing. And that's usually denoted by alpha. So whenever you see hypothesis testing, whenever you see the term alpha, I'm very sure you're not left in deep waters right now, right? Fantastic. And next we come to something called as the p-value. The p-value is basically the probability that we're trying to see. We're trying to understand if a t-statistics as extreme as your calculated value can be occurred if your null hypothesis is true. This is very important for you to know. So what happens when your p-value changes? When your p-value becomes very low, it means that you are ready to reject your null hypothesis. And once you reject the null hypothesis, it automatically means that your p-value is less than what? Less than what? Less than the significance level that we just understood, right? So significance level, p-value, null hypothesis, alternate hypothesis, you can see that all of these are linked in a chain. So once you start understanding one thing, like a domino, you have to understand the others or it's going to become pretty difficult for you to figure out, right? I think this is one of the reasons why, the domain such as hypothesis testing is usually seen as very complex. But as you can see from the moment, it was pretty simple, right? Fantastic. Now guys, let's take a quick look. In fact, let's take a deep dive into understanding what ANOVA is. And in fact, you might have heard of a lot of these terms that you'll see on the title here, but all of these are like really, really important concepts in the world of ANOVA. Now, there's something called as one-way mean and two-way mean, or one-way average and two-way average that you guys have to know about. Well, as the name itself suggests, one-way and two-way mean, it basically depends on the total number of individual variables, independent variables that you're basically trying to assess. We know that you can have independent variables, you have dependent variables, you apply a function on that, and a change in one will result in a change in the other. We already know this. But what happens is that, as the name itself suggests, one-way mean is basically telling you that you have only one independent variable that you want to assess. Let me give you an example. Think about you just trying to find your favorite brand of oats in your nearest supermarket. You're trying to look at anything else. You're trying to analyze and understand what's your favorite brand. Go there, pick up that brand, go home. That's one-way mean if you're trying to analyze the situation. Now, what happens in two-way mean is that here we have two independent variables that you have to think about, right? Previously, you just thought about maybe the brand, but now you say, hey, now I want to also look at brand, but I also want to look at the number of calories that each of these brands worth of oats is giving me, right? Maybe one brand is giving you a large amount of oats, but its calorific value is very less. So it's probably a bit more healthy if you're looking forward to losing weight or something. But the other one, maybe it's slightly higher in its calorific value. So you want to understand all of that. So here, you're not just comparing two brands, but you're comparing two brands alongside the calories that each of these brands in each of those packets or whatever that they're providing you, right? So you see, there are two independent variables you're tracking. When you're tracking two independent variables, what is it called? Two-way mean, right? Look at this again. When you just take a very complex concept, put it down into really simple understanding examples, I'm confident that all of you all can understand each and every one of these regardless of how beginner you are, right? Now, there's one more concept called as levels, or it's usually called as groups. Levels and groups mean the same thing. So basically groups, what they are is they denote what sort of deviations that are there in the same independent variable. Now, I know that sentence probably added more confusion to your learning. So let's go to the same example. Let's go to the same oats example that we were discussing. Let's just say that a level in your favorite brand of oats can be oats 1, oats 2, and oats 3. There are 3 levels for your oats. Now, another level that you want to maybe have in terms of its calories is to see if it's very bland in taste, has some sugar, or maybe has a lot of sugar. Let's just say that it's either bland, either it's sugarless, or it's with sugar. Now, when you take a look at the overall data, what does it look like? You have two groups, right? One, you have your favorite brand of oats, oats 1, oats 2, oats 3. There's another group or another level where you're trying to group it based on if it has no sugar or if it has sugar. So you'll see that you have two groups of data. One group has 3 individual levels. There's another group which has 2 levels. Now the first level is basically oats 1, oats 2, oats 3, where the second group and all the 2 levels that are associated with the second group are nothing but sugarless and sugar. So once you start grouping all of these things and putting them into a structured approach, that's when you call it as levels or groups. And again, with the same oats example, you're not only clear with what one-way and two-way mean is, but at the same time, you're also clear about what levels and groups is, right? So again, to reinforce the same concept a little bit more, to make sure you guys are thorough with this, consider one more example. Let's just say that you are a fitness trainer and you're trying to assess the weight loss in your clients. Now, maybe you've started working in a gym, you already work out a lot, you've decided to be a trainer, you're certified and all of that. And now you want to understand something. Let's just say that there are three groups of candidates, three groups of students or whatever that you're training right now. One group says that, they'll only diet and lose a lot of weight. There's another group which says, hey, I'm not going to diet, I'm going to eat, it's okay, but I'm going to keep exercising to make sure I lose weight that way. But there's a third group which does both. They say, hey, we're going to diet also and we're going to exercise also. Now you want to understand, which group is more efficient in terms of burning calories. And at the same time, it's very easy to say that the group that is dieting and exercising can lose a lot more weight. But you have to understand here that your dependent variable is the number of calories that you burnt and number of calories that you actually consumed, and you have to do it on a per day basis, right? If you consume less calories and burn more, you lose weight. If you consume more calories and burn less, you gain weight. Pretty simple, right? So once you start building each of these relationships, one under the other, one below the other, one below the other, the concept called as nested ANOVA comes into the picture. Because right now your groups not only are just individual groups on their own, but these groups have certain hierarchical structure that is associated with them, right? One group only diets, one group only exercises, but then there's a combination of these both who say, hey, now we have another group who will both do exercise and they will be doing certain dieting as well, right? Fantastic. Now, once you're clear with that concept, there is another concept called as replication in ANOVA that you should know. What you can do is that while you're performing certain testing, you can actually have certain data points, and instead of just running it once over your data, what you do is you replicate your test with multiple different groups of data. Once you do that, you will have a better way to perform in-depth analysis, right? Now, let's just say that you're performing two-way ANOVA, wherein you have two different groups and each individual groups are doing more than one task. Two groups, each group doing more than one task. Now, to give you an example of what replication would mean, think of it that there are three groups of college students from three very different colleges taking three different tests. Three colleges, out of which three different students, out of which they are taking three different tests. Now, if you have to compare and perform some analysis, you're going to require this concept of replication to figure out on the whole who performed better at what, right? If you just directly compare it, there are three different tests from three different students, three different colleges. You're not going to be able to make any concrete assumptions there. Right? So guys, that all of these things that I just spoke are very, very, very important for you to understand, especially in the world of ANOVA, because using on to that is what you will later build upon.
Till now in this video, we have covered what is ANOVA test, what are some of the terminologies related to ANOVA test, why do we do ANOVA test. Now let's see what is F statistics. So what is F statistics? F statistics is a value which is used to find out if there is any significance difference between the two mean of the population. So what we mean to say, suppose we have two samples, 1 and 2, and we want to know whether there is a difference between the mean of the two or not. So for that, what we will use F statistics. So what is F statistics? What is the formula for that? So F statistic equals to variance of the group means divided by mean within the group of variances. What are the variance? Variance are measures of dispersion. Larger the F statistics, greater the dispersion between the two population. Now, what is the range of F value? So whenever we calculate the F statistics or F value, we get a number which ranges from 0 to an arbitrary very large number. So what is the interpretation of F statistics, or we can say what is the use of F statistics? F statistics is used to reject or accept the null hypothesis. If the F value, your calculated F value, is greater than the tabular F value or critical F value, then you can reject the null hypothesis. So what we can say, if your calculated is greater than your F tabular, then we can reject null hypothesis. But if we have something like that, f calculated is smaller than f tabular, then in that case we can say fail to reject null hypothesis, or we can say null hypothesis accepted. Okay, so when null hypothesis accepted, that means the means of the two groups are same, and if it is fail, if we are accepting the null hypothesis, then in that case we can say that the mean of the two group is same. Or when we are saying that f is rejected, then in that case we can say the mean of the two are not same. So now moving on to the next slide, f distribution. So what is f distribution? F distribution is a continuous probability distribution of f statistics. Whenever we perform f statistics for let's say various number of times, what do we get? We get a distribution of f statistics. So this distribution can be something like that. So f distribution has minimum number 0 variable and it has no maximum value. So we can say it has infinite as a maximum value. F distribution is a testing of whether two samples have same variance or not. F distribution is the ratio of two chi-square tests, two independent chi-square tests within the different degree of freedom. The highest peak of distribution is always right to the 0 value. So what is F distribution? As we said, if you see in this red circle, this is known as critical region. Okay, so if your f value lies in the rejection area or the critical region area, the f value which you calculate using the f statistics formula, if it lies towards this red region, then you can say you can reject the null hypothesis. Or else if the value not lie in the rejection area, then you cannot reject the null hypothesis. So from this diagram, what we can say, whenever we plot the f statistic values, so what do we get? We get two region. One is this and the another one is this. So this region is known as critical region. Okay, so now in this critical region, if your f value, the calculated f value, lies within this range, within this right side, then you can say hypothesis reject. You can reject the null hypothesis. Or if it lies towards this left of the red region, then you can say accept null hypothesis. Okay, now let's move on to our next topic, that is application of f test in ANOVA test. So what is ANOVA test, or what is the application of ANOVA test? First we see ANOVA, analysis of variance test, is used to determine whether the mean of three or more groups are different or the same. In order to test the equality of means, or in order to check whether the group of mean of three or more groups are same or not, we take the help of f test. So we calculate the f statistics. So when we do the f statistics, we get f value. With that f value, we compare this f value with f critical, or we can say f tabular. And if our f value is greater than this one, we can say we can reject the null hypothesis. Or if it is not greater than, or f value is not greater than the f tabular value, we are failed to reject the null hypothesis. So what we can say, another thing which we can consider here is that f statistics. F statistics is test statistics for ANOVA test. Now, moving on to next topic, that is types of ANOVA test. Basically, we can divide the ANOVA test into two parts. One is one-way ANOVA test and the second one is two-way ANOVA test. So what is one-way ANOVA test? In one-way ANOVA test, we can say that there is one independent factor which influences three or more groups. Let's take an example and understand it. Suppose there is a disease for which we have three medicines: medicine A, medicine B, and medicine C. And we can see that there are days to recover. Let's say if medicine A is taken 5 days, some patient took 6 days, some patient took 7 days. Similarly, this took 10, this took 15, and this took 2 days. Similarly, C took, let's say, 9 days, 7 days, and 1 day to recover. So here all the three medicines, these are nothing but independent variable. Okay, so there are three types of independent variable that are nothing but the medicines. So ultimately we have one independent factor, that is medicine, on which days to recover depend. So here we can say that when we have one independent variable and one dependent variable, then we can say that the test we should apply here is ANOVA test. Now let's move on to the next type of ANOVA test, that is two-way ANOVA test. In two-way ANOVA test, there is two independent factors which influences the three or more groups. Okay, one independent factor influences three or more group column wise and the other influences row wise. So now let's take an example to understand this. Suppose there are department and universities. Let's say it is IIT Delhi, IIT Madras, IIT Bombay, and IISc Bangalore. Okay, sorry, IISc Bangalore, and there are three departments. One is CSE, another one is mechanical engineering, and another one is electrical engineering, and their annual package. Let's suppose the students get placed, what is the annual package in across the different universities and across the department. Let's say 18 lakh, 20 lakh, 14 lakh, 25 lakh. Let's say 15 lakh, 16 lakh, 12 lakh, 19 lakh. Then 19 lakh, 18 lakh, 10 lakh, 7 lakh. So here we can see that there is college, or we can say universities, and department. So department is a independent variable and this college is another independent variable. So what we can see here there are two independent variables. One is department and another one is college, and this is influencing or impacting the annual package, or we can say the students who gets placed, their average salary across the groups. Okay, so here what we will get, we will get two null hypotheses. One will be across the rows and one will be across the column. So one will say that there is no impact of department on the average annual package of students, and another will be there is no average there is no influence, or we can say impact of annual package on the college of the college on the annual package of student. So here we will get one for row and one for column.
Now, here's another concept called as one-way ANOVA that we can quickly discuss. Now, one-way ANOVA is very simple, guys. It's very straightforward. What we do here is we try to compare two averages or two different means from what? Two different unrelated groups. That's it. The null hypothesis in this case means that the two means will actually be equal. And if you have to have a result and you want to say, hey, my result is significant in one-way ANOVA, it means the two means that you have calculated should not be equal to each other. Think about it for a second. We already discussed this. What happens if two means are equal to each other? It means that you're not finding any variation that exists between them. Your analysis is in vain. But what if you perform one-way ANOVA as you just understood, and you have calculated two different means from two different groups having two different independent variables, and then you find out that their means are very much different and not exactly the same. That's when you say, here is the variation in analysis that you have performed, and guess what? That serves to be the heart of one-way ANOVA, right? So as always, let me give you some examples to help you understand when you should use one-way ANOVA. Let's take the first example. Let's just say that there is one group that has been one big group of data or anything that, let's just say people, one big group of people that have been split into multiple small groups, and you are trying to understand the effects of coffee, let's just say, on weight loss, right? Now you already know that coffee increases your energy, it increases your metabolism and whatnot. So increase in metabolism means increase in fat loss. So you want to understand what is happening with the black coffee drinkers and people who prefer milk in their coffee and people who prefer milk and sugar in their coffee. You want to understand who will lose more weight based on this. If you want to perform individual analysis like that on these independent outcomes and variables, you use one-way ANOVA. Fantastic, right? Now, there's another example. Let's just say that you want to do further subgrouping from an example 1 to C to understand, to figure out if your candidate is normal in terms of weights or if they're overweight, underweight, or obese. So what do? You just don't look at, you don't look at the scale without looking at the person and saying you're overweight, right? You have to have something to compare to. You need an ideal version of maybe a fit person to compare it to. And once you start grouping all of these terms to find out if a person is actually directly comparing or not, what is the variation between a perfect candidate and a candidate who joined your gym to lose weight? That variance is where I'm very sure the workouts lie in. That is what you're trying to analyze. And with respect to one-way ANOVA, you can do a brilliant job with that, right? So ladies and gentlemen, that is one-way ANOVA. Now here is two-way ANOVA. Well, two-way ANOVA is a really interesting concept, and it's a very, very similar concept to one-way ANOVA, but it's more important, it's slightly different. I'll tell you how. Now, the important thing you have to know about two-way ANOVA is that it's actually a direct extension of one-way ANOVA. It is add-on, it is built upon one-way ANOVA, and here instead of one independent variable, what do you think happens? Of course, you already figured it out. You have two independent variables at hand, right? So if you're performing an experiment and you know that it has a quantitative outcome, it has a number, it has a quantity as an outcome, and you have two variables that you have to assess and analyze, two-way ANOVA is exactly what you would use. Give you an example. Let's just say that you want to assess if your expensive product, let's say you're an expensive product manufacturer, and you want to see if it is sold worldwide, and you want to see who's buying your new product that you might have sold. Now, I've said that it is expensive means that you're trying to figure out, maybe you want to understand which gender prefers your product more, or you want to understand which income bracket that your customers usually fall in, right? Now, there are so many really, really expensive phones and clothes and whatnot out there, but it doesn't mean that everyone is going up to pick up that, right? Based on your own income bracket, based on your own preferences, you'll probably prefer dressing up differently, and maybe you don't need a $10,000 wallet to go about everywhere, right? Maybe you cannot afford a $10,000 wallet to go about beginning with. Think about it for a second. So when you have to assess situations such as that, of course, I gave you a very simple example, you are going to require two-way ANOVA. Now, to perform two-way ANOVA, since you have two independent variables out here, there is a very important concept you have to understand. Here, there are certain assumptions which have to hold true. First of all the groups must have equal sample sizes. If one group has a ton of data, the other group has small amount of data. If you try to compare it, of course, your data can be skewed in one direction. It's not a fair comparison that you're doing, correct? Similarly, the variances in the population must be the same, as in how much the data varies. You cannot pick up one group of data which is closely assigned to people who are losing weight, and you cannot bring in another group of data to say that, hey, I have 10% of people here who want to lose weight, but rest all want to gain muscle and not lose a single kilo of weight. Well, you have two very, very different data groups which vary a lot, so you cannot compare them, correct? So you have to take care of that. And each individual value that you have at hand that you're wanting to compare, this should be very different and independent from the other. One person's workout should not affect the other person's workout as well. That is a condition that you have to keep in mind when you're looking at two-way ANOVA. And overall, when you take the entire data, overall, when you just have the population at hand, the data you have must resemble something called as a normal distribution. A normal distribution is basically a bell-shaped curve. Again, I'm very confident that you will know probably what a normal distribution is, right? So your overall data, every single data point must conform to I'm not saying that it has to be a normal distribution. We're saying that it has to resemble the characteristics that is posed by data points which come under normal distribution, right? So this is super important for you guys to know.
Now let's do some calculation of ANOVA test on paper. So here in this example, we will see examples of one-way ANOVA test and two-way ANOVA test, and based on that we will see how we can solve this. So let's suppose there are three medicines were given to patient who are suffering from some disease. We are not going to name the disease. Below table is showing the amount of days it takes to get recovered. Check whether there are all three medicines have same impact or not. So before we proceed, since there is no alpha is not given here, so we will consider alpha as 0.05. And for this example, here we can see that there is only one independent variable, that is column wise, that is medicines, and here in this row wise we don't have any independent variable, rather we have days to recover. Okay, so medicine 1 for some patient it took 8 days, for some patient it took 7 days, for some it took 17, 14, 7, 11, similarly for the other medicines. So now let's see how we can solve this. So as a first step, what we will do, we will calculate the sum of medicine 1, medicine 2 and medicine 3. So sum of x, sum of y and sum of z are 50, 40, 60. Next step, we will calculate the mean of x and y and z. So mean of x is 10, mean of y is 8, mean of z is 12. Now we will define our hypothesis. So our null hypothesis says that all medicines takes equal time for patient to recover, or we can say mean of x is equals to mean of y is equals to mean of z. On the other side, the alternate hypothesis says that all medicines does not take equal time for patient to recover, or we can say there is one medicine which is not whose mean is not equals to the rest of the two means. Okay, so we have defined our null hypothesis. Now next move on and do the grand total. So we will summarize sum of x, sum of y and sum of z. 50, 40, 60, that is nothing but 150. Now we will calculate correction factor. So what is correction factor? So whenever we are performing some test, there can be some instrumental error or there can be some manual error. In order to remove those error or in order to penalize those errors, what we do, we add a correction term. So correction term is nothing but grand total divided by the total number of values. So 150 square divided by 15, that is 1500. Now next we will calculate sum of squares between samples. So whenever okay, let me explain you what is between the sample and what is within the sample. So here we have some values. Okay, so when we say between the sample, this is x, this is y, this is z. So whenever we are calculating sum of squares with between samples, so this is one sample, this is two sample, this is three sample. So we will calculate between these. So this is sum of x squared divided by n plus sum of y squared divided by n2, sum of z squared divided by n3 minus t squared divided by n. That is 50 squared by 5, 40 squared by 5 and 60 squared by 5 minus 1500. That is our correction factor. So it becomes total 40. Now let's calculate what is degree of freedom. So as we have discussed what is degree of freedom. So degree of freedom is nothing but the number of columns minus 1. So here we have 3 columns. So our degree of freedom will become 2. Now let's calculate total sum of squares. So total sum of squares is sum of x square, sum of y square, sum of z square minus t square by n. Here if you see carefully, you will identify we are not dividing each terms with n1, n2 and n3. So while we are calculating the sum of squares, we don't divide it by the number of terms. So this is 1500 plus 1600 plus 3600 minus 1500, that is nothing but 6200. Now let's calculate sum of squares within the sample or the error factor. So when we are calculating sum of squares within the sample, that is nothing but inside the sample. So that is our the formula for this is SST minus SSC. So we have calculated our SST as 1600. Our SSC is nothing but 40. So this becomes 6160. Now let's calculate mean sum of squares between the samples or MSC. MSC is nothing but SSC minus divided by n minus 1. That is 40 divided by 3 minus 1 equals to 40 divided by 2. That is nothing but 20. Now next we will calculate mean sum of squares within the sample. So MSC is equals to SSC divided by n minus c, where n is the number of data points and c is the number of columns. So MSC is equals to 6160 divided by 15 minus 3, that is 6160 divided by 12, that is nothing but 15513.33 or 1500 and 513.33. So now as a 12th state, we will calculate the F value for this. So we know F value is nothing but MSC divided by MSC. So our MSE is 513.33 and MSC is 20. So that is 513.33 divided by 20. That becomes 25.66. Now we know that what is our calculated F value. So our calculated F value when degree of freedom is 2 and n minus c is 12, we can say that it is 25.66. And with the help of the expected value or the tabulated F value is F2 and 12, that is 3.89. So from this we can see that this 25.66 is much larger than this 3.89. So we can say that we can reject the null hypothesis, or if we remember the F distribution plot, we can say that this number lies in this right portion. So this is our F value is lies within this range. So we can reject the null hypothesis. Now let's move on to our next example. So here we are taking an example of two-way ANOVA test. So in this example, let us consider that there is there in a town there are 4 outlets for a pizza outlets, and there are seasons: summer, winter, and monsoon. So in for the company's performance, or the profit which the company earns in all the across 4 outlets are: for A 36, 28, and 26 in summer, winter, and monsoon. Similarly for B 36, 29, 28. For C 21, 31, 29. For D 35, 32, and 29. If we see the seasons total, that will become: for summer it is 36 plus 36 plus 21 plus 35, that is 128. For winter it is 120, and for monsoon it is 112. Similarly for outlets, some if we can say, then for A it is 90, for B it is 93, for C is 81, for D it is 96. And if we see the total sum of the terms, or we can say all the sum of the A, B, and C and D across all the 3 monsoon, we can say that it is 360. Now how we can say this example is a two-way ANOVA test? Now here we can see clearly 2 things. One is outlet and another one is season. So season is an independent variable, and this one is also an independent variable. So when we have 2 independent variable, we can say that the test is a two-way ANOVA test. So first we will discuss, or we will define our hypothesis. So we will define our hypothesis based on outlet level and season level. For an outlet level, our null hypothesis says that there is no significant difference in the performance of outlets. An alternate hypothesis says that there is a significant difference in the performance of outlets, or we can say there is one outlet whose mean of the performance is different from the other twos. Then at a seasonal level, we can say null hypothesis as there is no significant difference in the seasonal cells. Alternate hypothesis says that there is a significant difference in the seasonal cells. Now we have our hypothesis defined. So now let's move on to our next step. So first step is coding a value. So here, if you see carefully, we can say that most of the values, or if we average out, we will get the 30 as an average. Okay, so since we are getting 30 as a value, so what we can do, and if we start calculating with this 36, 21, 35, then it would become very difficult, or we can say it would become a lengthy process to cover the total mathematics. So what we have done here, we have coded the values. So we have subtracted each value, each entries with 30. Okay, so 36 minus 6, 36 minus 30 is 6. 36 minus 6 is 36. 21 minus 6 is 21 minus 30 is minus 9, and 35 minus 30 is 5. Similarly, we will calculate for all the other values, and we will calculate the seasons total, and we will calculate the outlet total similarly. So now we have a very smaller values with which we can do the calculation easily. Sometimes you may not find a value which you can subtract or divide or multiply in order to do the maths easy. So in that case, we cannot perform this step. In such situations, we will go with the normal process. So our next step, calculate the grand total. So our grand total is 0. Now let's calculate what is the correction factor, that is t square by n. That will also become 0. Now next step, we will do the calculation of sum of squares between the cells, or we can say SSC, sum of squares of columns. So our SSC will become 0 divided by 3 plus 3 square divided by 3 plus minus 9 square divided by 3 plus 6 square divided by 3. That becomes 42. Now we will calculate the degree of freedom for column wise. So that is C minus 1. That will become 4 minus 1. Since we have 4 columns or 4 values A, B, C, D. So our degree of freedom will become 3. Now let's calculate sum of squares of seasons, or we can say row wise. Sum of square of rows. 8 square divided by 4 plus 0 divided by 4 plus minus 8 square divided by 4 plus 0. That will become 32. Now as a next step, we will calculate the total sum of squares of total. That is sum of A, sum of B, sum of C, sum of D minus correction factor. That is 56 plus 41 plus 83 plus 30 minus 0. That is 210. Now next we will calculate the total degree of freedom. That is, since we have total 12 values, so 12 minus 1 will become 11. Now let's calculate sum of squares within the sample, or SSE. So SSE is nothing but SST, or sum of squares of total, minus SSR, the sum of squares of row, and sum of squares of columns. So 210 minus 42 minus 32, it will become 136. Now next step, we will do the calculation of degree of freedom within the sample. So our formula for the degree of freedom within the sample is column minus 1 multiplication of row minus 1. That is 4 minus 1 into 3 minus 1, which becomes 6. Now as a next step, we will calculate the F ratio. So our F ratio will become, before calculating the F ratio, let's just tabulate all the values. Source of variation, that is between the sample, between the row, within the sample. Next, we will calculate the sum of squares, that is SSC, SSR, and SSE. Degree of freedom, C minus 1, R minus 1, C minus 1 multiplication of R minus 1. Now, next step, we will calculate the mean of sum of square. So, SSC divided by C minus 1, SSR divided by R minus 1, SSC divided by C minus 1 multiplication of R minus 1, which will become 14, 16, and 22.67. Now we will calculate the F ratio for column, that is F of degree of freedom, that will become the 6, C minus 1, R minus 1, the total degree of freedom, comma, degree of freedom of column. So it will become MSC divided by MSC, which is 22.67 divided by 14, that is 1.61. Similarly, we will do the calculation for F ratio row wise, F 6,2, that is MSE divided by MSR, 22.67 divided by 16, that is 1.41. Now we can say that the type is column wise row of F value, row wise F value. What is the value of F ratio? That is 1.61, 1.41. And our tabulated, or the calculated earlier calculated row F ratio is 8.94 and 1.93. So here we can say that 8.94 is greater than 1.61, or F calculated is lesser than F tabulated in both the cases. So we can say that null value accepted, or we can say that the mean of the sum of performance of outlet across season is same, and the sum of performance across the outlets mean is also same. Now let's move on to our next topic, that is ANOVA test on Excel. So here in this example, we will be solving an ANOVA test using a spreadsheet, either Google spreadsheet or Microsoft Office Excel. So without wasting any time, let's open our Excel sheet. Now let's take an example of medicine 1, medicine 2, medicine 3, and the impact of them on recovering of patients The same example we did it in the earlier slide text. This is medicine 1. Medicine 1, for some patient it took 19 days, 12 days, 19 days, 14 days and 10 days. Similarly, medicine 2 took 10 days, 14 days, 10 days, 10 days, 14 days, and medicine 3 took 11 days, 15 days, 13 days, 14 days and 13 days. So our table is here with us. Let me add a border to it. Yeah. Now we will go to our data and we will go to our data analysis. Click on data analysis. Now we will see on the top there are three options: data ANOVA single factor, ANOVA two factor with replication, ANOVA two factor without replication. So here we will, since this is a one-way ANOVA test, so we will took the ANOVA with single factor. Now select this. Now we will select the input range. So we will select the entire sheet, entire table. Now we will mark label in first row, column wise. Alpha will remain the 0.05. Now set the output range. Where do we want to see the result? So just we need it here. So now we have our model summary ready. ANOVA test with single factor. The summary for medicine 1, medicine 2, what is the count of values, what is their sum, what is average, what is variance. Now we will calculate the ANOVA, we see the ANOVA result, F score, P value and the F critical. So here in this example, we can see the F value is 1.62 and our F critical is 3.88. So here we can say that since F critical value is greater than F crit is greater than F value, so we can say that we can accept the null hypothesis, or we can say we are failed to reject the null hypothesis. Now let's take another example where we will be solving two-way ANOVA test example. Now let's suppose there is a data, that is we have a data of various institutions and their annual package across the department. So we can see that there are IIT Delhi, IIT Mumbai, IIT Bombay, IIT Madras and IISc Bangalore. And the departments for which we are checking the packages, that is CSE, mechanical engineering and electrical engineering. So what are our null hypothesis and alternate hypothesis? For the institution label, we can say that we have a null hypothesis that there is no impact or there is no difference in the package across the institutions, or we can say the mean of average package is same mean of package of all the three IITs and IISc is same, and on the column wise, or we can say for the row wise, we have CSE, mechanical and engineering, electrical engineering. So we can say that the null hypothesis says that there is no significant difference in the average package of CSE, mechanical engineering and electrical engineering, and the alternate hypothesis says that at least there is one value for which the mean package is different. Now let's calculate. So we will go to data. We will go to data analysis. We will choose ANOVA two-factor without replication. Okay. So we will do the label. So this is our label. Alpha is this. Now we will have this as our output. click on this. So now we can say that row wise count sum, average and variance, and column wise count sum and average and variance. Okay. Now here we have two source. Row wise, this is row wise F score, and this is column wise F score. So here in both the cases, we can say row wise and column wise, the F scores are 0.70 and 0.61, and the F critical value row wise and column wise are 5.14 and 5.745. So we can say that we are failed to reject the null hypothesis in both the cases, or we can say that there is no significance difference in the annual package of uh, students across the institution as well as across the department level. Now let's move on to our next topic, that is ANOVA test using Python. So here in this test, we will be solving a ANOVA test using a Python. For that purpose, we will be using Anaconda and Jupyter Notebook. I would highly recommend you, if you have not gone through what is Anaconda, how we can install Anaconda in our system, or what is Jupyter Notebook, I would highly recommend you to go and watch the GL playlist where you can find videos related to Anaconda and Jupyter Notebook. Here in this exercise, we will be using Pandas, SciPy, NumPy. If you have not installed that packages, please install those packages before executing the codes. For that, you will need to use pip install pandas, pip install SciPy, pip install NumPy. If you don't know about what is pip and how this pip command works, I would again highly recommend you to go and watch the GL videos for what is pip and how we can install packages into our environment. Now we have our Jupyter Notebook file open. So here in this example, we will be solving one-way ANOVA test. So for that, first we will load pandas package, and then we will load the data which is stored in CSV file into a data frame. Now execute this. Now the data has been loaded. And before moving forward, I would like to again tell you one step. Whenever we are running any step in Jupyter Notebook, either you can use this run command, or you can use simply shift plus enter. Your code will get executed. The cell is executed here, and now we can see the DF. So now we have our data ready. Now we will use the melt function to change the or to transform the data into something like that index, temperature, and values. Now execute this. Once we do this melting, we will see that there is a temperature index, there is a temperature column, and corresponding values to it is there. Now we have all these things ready. Now let's go and plot this using matplotlib and cbarn. So here we are plotting it using boxplot. So let it get executed. So we can see A, B, C, and D. So here we can say that what do we get about, with the help of boxplot? So with the help of boxplot, we can see here that there are certain values which are outside of the boxes. Let's suppose this point or this point. So what we can understand that these are nothing but an outlier. So based on the type of use cases or based on the problem statement, sometimes we need to remove the outliers. So either we directly remove them, or we do the data transformations using some normalization technique or standardization techniques. If you are interested to know about them, you can go and watch the playlist about feature engineering or feature scaling in GL playlist. Now let's move on to our next step. So here we are using a SciPy stats function as a stats. So with that, we will calculate the F value and P value, and then we will be using stat state model, and then we are using the OLS model to to find out the ANOVA table. So now let's do that. So before do that, let me tell you what we are doing here. So we are calculating this F one-way ANOVA as stats dot F ANOVA, then your DFA, DFB, data frame C, data frame D. So we can see here this data frame A, data frame B, data frame C, and data frame D. So we will pass this values and we will create a ANOVA table out of it. So now we can see that our F value is coming 17.49281, and our P value, corresponding P value, is 0.000026, which is very small to our alpha, that is 0.05. So we can say that from this, what we can interpret that the P value obtained from ANOVA analysis is significant, or we can say is smaller than 0.05. Therefore we can say that there are significant difference of temperature within the different districts, okay, or within the different values. Now let's try and solve a two-way ANOVA test. So for that we will be using data that is known as a two-way ANOVA CSV. Let me execute this. Now we can see that. Let me just get the data frame. Let's see the data frame. So we can see here student name, first year marks, second year marks, third year marks, and fourth year marks. So we have this data. Now melt this data and we can see it something like that: student name, year, and marks. Okay. Now we will do the box plot for this. So we can see the box plot for first year, second year, third year, fourth year for A, B, C, D, E, F student. Now again we will calculate the ANOVA table. We will calculate the ANOVA table using the OLS function. Now execute this. Now here we can see that the column wise student, year, we can see that the P values are significantly very high to 0.05. So in that case we can say that the mean of the students score is same, and the mean score of student year wise is also same. We are failed to reject the null hypothesis. Similarly, we can apply ANOVA test on various data similar to the step which we have done here. Moving on to our next topic, ANOVA test using R. So in this, we will be solving an ANOVA test using R programming language. So without wasting any time, let's open our Jupyter notebook and let's get started. Now we have our Jupyter notebook opened. So we have opened the file ANOVA test using R. So here in this test, we will be using one diet data CSV file. So let's get started. So first we will read the CSV file using read.csv. Header is equals to true. That means first column will become our first row will become our header, and it is separated by comma since it's a CSV file. So now let's execute it. So this is our data, that diet on first week and on second, on third, similar to that. Then week on a diet on week 1, diet on week 2, and diet for like first, second, third variable. Okay. So now let's calculate weight loss. So weight loss is nothing but the difference between the first week's weight minus the second week weight. So let's calculate this. Let's just print this out. So now this is the list of values which we get. So now let's set up a null hypothesis. So our null hypothesis says that the population means are equal, or we can say the weight of population is mean weight of population across the different groups is same, and the alternate hypothesis says that at least one population is not same as to the equal to the other two population. So we have our this thing ready. Now this is not required. I'll just remove this off. So let's just before you're doing the hypothesis testing, let's plot this bar. So from this bar plot, what we can say, from here we can see that type 1, type 2, type 3 and their weight loss. Okay, so we can see that gradually there is increase in the weight loss across the group. From one group the weight loss is higher in 2 and which is higher in 3. So from this plot even we can understand that the mean is not same. But to ensure ourselves, let's try and do an exam to the test. So we will create one more thing that this diet will become a factor. So factor is nothing but a categorical variable. In R, whenever we want to define a variable as a categorical variable, what we do, we write it as factor. So now we have created it. Now we will use the ANOVA function. So inside that we will be using weight loss, my diet, okay, and the data is my data, and we will get the table for that ANOVA test using the AOV function, and we will summarize it using the summary function. So now when we do this, what we can see here, the p-value is 6.55 and our this p-value for this is coming which is very smaller than 0.05. Similarly, we can see here there is 2 star. That means it is less than or equal to 0.01, the significance level. So from this information, what we can say that there is a significance difference between the weight loss across the group, or we can say we can reject the null hypothesis. Now let's move on to our next example. So for this example, we will be using predefined data which is stored in R, that is tooth growth. So our tooth growth has this data that there is a factor 1, that is supply, dose and length. Okay, so this is factor, this is double and this is double. So now let's define our null hypothesis. The first null hypothesis says that the mean of the observation groups by factor 1 factor are same. The mean of the observation grouped by the other factors are same. And the third hypothesis is there is no interaction between the two factors. So in order to execute this, let's use this function res.aov2. We will store it as a variable to AOV function, length, supply, and our factor is nothing but dose. So we are making it a factor variable and the data is tooth growth. Now execute it. So from this, what we can get, the F value is 15.57, 90.00, 4.107. And these stars are interpreting or giving us the information that these are the coefficient significant codes, or the significant value is for this F value is smaller than or equal to 0.05. In this case, if you see, the PR is very small. It is 0.00023, which is very small as compared to 0.05. Similarly, this one is also, the second one is also very small, and the third one is also very small, 0.02. So here what we can say that we can reject the null hypothesis, or we can say that there is at least one group for which the mean is not same across the column wise and across the row wise. Now let's move on to our next topic, that is difference between ANOVA test and t-test. So in t-test, we know that the t-test is a type of inferential statistics which is used to compare the means of two population. So there is a constraint in t-test, that is, it is applicable to for two population only. Whereas ANOVA test is also an inferential test used to compare means of three or more population. Moving on to the next difference, the test statistics for t-test is sigma bar minus mu divided by s divided by under root of n. Whereas for ANOVA test, the test statistics is f statistics, or we can say the f value, that is the f statistics of ANOVA test is between the sample variance divided by within the sample variance. Okay, between the sample variance and within the sample variance. The third difference is t-test is used for hypothesis testing, whereas the ANOVA test is used to measure the deviation between the populations. So these are some of the important differences between t-test and ANOVA test. Now let's see some of the applications of ANOVA test. So basically, ANOVA test can be applicable in case of when we want to determine the relation between a categorical and a numerical variable by testing the differences between their mean. It is also used to determine the statistical difference between the two or more groups. Now let's discuss some of the limitations of ANOVA test. So ANOVA test needs all the data should be uniformly distributed. If the data is not uniformly distributed, we cannot implement that. The second limitation is the data sample used in ANOVA test should be random. The third thing says that the data sample should be independent. So what does this mean? Uniform distribution. So we have already discussed, or we know that ANOVA test is nothing but it's a parametric test. Parametric test says that the distribution should be normal. So what is normal distribution? Normal distribution says that the mean is 0 and the standard deviation is 1. This will become -1. This will become -2. So whenever we get this kind of a distribution where the mean is 0 and the standard deviation is 1, we can say that this is normal distribution or uniform distribution. For such kind of data, we can implement ANOVA test. Now let's discuss few advantages and disadvantages of ANOVA test. So let's first discuss the advantages. So the first advantage is ANOVA test is robust in nature. The second advantage says that ANOVA test reduces the random variability. It has few disadvantages as well. One of the disadvantages says that ANOVA test is used to determine whether one group of data is different from the others or not. However, we cannot determine which group is different from the other one. So let's understand that. So what our null hypothesis says that mean of A is equals to mean of B is equals to mean of C is equals to mean of K. Whereas H1 says that at least mean of A is not equal to mean of B, is not equal to C, is not equal to D, similarly is not equal to K. So here we can see that either we can say that the mean are same or they are not same, but we cannot say that which particular group's mean is not same or not similar to the other one. So this is disadvantage of ANOVA test.
Well, with that, we are done with one-way ANOVA, we are done with two-way ANOVA. We have one more concept called as MANOVA. Well, what is MANOVA? MANOVA is basically analysis of variance, but the M here stands for multiple. So in this case, in MANOVA, you'll have multiple dependent variables of that you have to perform analysis on. But one advantage is that just like regular ANOVA, this will also help you to check if your dependent variable has either changed when you worked on it or if it remained constant when you're manipulating the independent variable. Now, changing the independent variable usually will not, affect, or not usually, in some cases it does affect or not affect the dependent variable. But now you want to find out if it does, if a change in your dependent variable will cause certain change, basically when you have manipulated the independent variable, right? So let's just think of independent variable as a knob that you want to twist around and play. So every time you twist around this independent variable knob, you want to understand if your dependent variable changed or not. And to do that, just like regular ANOVA, with here, in fact, you'll have multiple dependent variables. That is why we require MANOVA. You might be asking a question right now. You might say, hey Anirudh, one-way ANOVA is over, two-way ANOVA is over. We realized a lot to do with multiple independent, dependent variables, everything. But why do we even require MANOVA? Where is it critical to use? Well, whenever you're trying to understand the interaction that is happening in between your independent variables, you can only figure out the difference between these variables. But if you have to understand what amount of interaction exists between each independent variable, you're going to require the concept of MANOVA. And it's the same for dependent variables as well. You want to understand what amount of interaction is happening, especially if it's a dependent variable. It means that there will be certain changes when you mess around with something else. So what is the level of interaction happening? When you change certain things, what are the actual things that are being reflected in the change? What is the interaction there? To understand that, again, it's required, right? Now, one more question. Look at this last question. This is probably the most important aspect of MANOVA, because it is telling you that if you have to do any changes on your independent variables, does this have a say on your dependent variable? Now, in some cases, it might have that you change something in your independent variable. It had a little bit of a change in the dependent variable. But now you say, hey, all these little bit, I really don't care. I want to check if there's a significant effect on my dependent variable. Maybe you change a little bit of your independent variable and your dependent variable changes like a lot, right? It happens in mathematics. You know that. So understanding what and why and will anything happen, first of all, is basically why MANOVA is a very, very important concept. Now, let me give you a quick example to give you a bit more clarity of the topic. Let's just say that you want to find out if there was any difference in study material for maybe like social science or maybe mathematics, to see how it might have affected the scores of the people who have taken social studies and social science and math tests, right? Now here you have two variables at hand, two dependent variables at hand. And what happens if you use ANOVA? If you use ANOVA, you will know that these two variables, you can find out all the means, you can find the grand mean, and you can find the F ratio, you can find everything between data variance and all of that. Instead of actually using one single F value and knowing that it might not give you the result you're looking for, when you use MANOVA, it will basically help you maximize all the differences that exist. Now, if you're a person who wants to find out the difference in the scores to see if your study material has any importance to say, what will you be after? You'll try to prove that there is maximum difference in it, or you'll try to find out what is the difference, right? So your goal is to maximize these group differences. ANOVA will not help you do that because it will give you one F value, but using MANOVA will do just that, right? So you know now everything from one-way ANOVA, two-way ANOVA, MANOVA, and a lot more.
Let's discuss what are the things we have covered. So now after completing this course, we are knowing that what is ANOVA test. So ANOVA test tells you whether the group of 3 or more are there and their mean is same or not. So we know that when we can use ANOVA test. We also got to know some of the terms related to ANOVA test. Then we discussed few applications of ANOVA test. We also discussed the type of ANOVA test. We also see what is F statistics, what is F distribution. Then we discussed how we can calculate ANOVA test on paper, on Excel, using Python programming language, using R programming language. We also discussed few limitations of ANOVA test. We also discussed some of the advantages and disadvantages of ANOVA test. So I hope you enjoyed this video, and now you have a better understanding of what is ANOVA test and how we can apply ANOVA test and when we can apply ANOVA test. So that's about it from this video. I hope you enjoyed this video, and now you have a better understanding of what is ANOVA test and how we can apply ANOVA test, when we can apply ANOVA test, what are the applications of ANOVA test, advantages, disadvantages, and other things like that, whatever we have discussed in this course. Till then, thank you.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell. This is done to make sure you do not miss out on any of the new updates or video releases from Great Learning. And of course, guys, if you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, right? So make sure you share this video with your friends, colleague, and everyone who can make use of it. And at the end of it, make sure to comment on the video if you have any queries or any suggestions, and I'll be more than happy to respond to all of your comments.